Next, we are going to discuss why do we want this memory hierarchy. So this is the memory hierarchy. We have seen that for small capacity memory, like your L1 cache, it can be very fast. This is because small means fast. And then for the like your DRAM or flash, can be very large capacity. You can save a lot of data. But then to access those data, it will be slow. So simply you can think that the big means slow, fast, or small means fast. Why is that? Simply because you can think about the number of word lines, number of bit lines, or rows or columns. If you have a small array, the decoding is easier, right? You have short bit line, short word line, then it's easier for the signal to propagate from your decoder to the memory cell. So if you have small array, then you're going to decode faster, and then also it's faster to propagate your signal from the decoder to the memory location. But if you have a large memory, then it will take a long time to do the decoding and then localization of the data. So this is intuitive. Or in other words, you can think an analogy, right? If we have a small class like today, how many people here? Oh, only 8. So I can locate each of you very quickly, right? But if we have a large classroom and with all the 40 or 50 students in the class, then it will take longer time to locate each student. So similarly for the memory, so it's the same concept here. So you see the big gap between those two levels. If you want to balance the capacity and the speed, what you can do is to insert more levels into the hierarchy. That's why we have different levels in the memory hierarchy. So this is just to balance the capacity and the speed. Of course, you want to store the data that you frequently use in here, and then you back up the rest of your data, which are less likely to be used in the bottom levels. So that's the whole concept of the hierarchy. And then this also introduces a concept of the cache or perfection. So what does that mean? So that means those data you are going to process in the next cycle. So you need to prefetch those data from the lower level to here. For example, you are going to edit those pixels in the images in the next clock cycle. You need to load in those data to this local register. And then you can save the rest of the pixels in the other parts of the image to the lower level, because this is not large enough. And next, we are going to discuss locality of the data. So this is to look at the pattern of your data from the software programmer's perspective. Because one's recent past is a very good indicator or predictor of his or her near future. So if you look at the memory data pattern in the system, there are two kinds of locality. One is temporal locality. If you just did something, it's very likely that you will do the same thing again soon. And the spatial locality, if you did something, it is very likely you will do something similar in the related space. So that means in the adjacent space or neighbors. So what does this mean? We can use a very simple example of the software program, because many programs are composed of loops, right? So here, for example, this is a very simple piece of code you may write in your preferred language. And this is a for loop, right? And you are doing the summation of this vector. And you are going to change the index from 1 to n. And in each cycle, you are going to increase the index by 1. So that means in the adjacent clock cycles, we are going to process the data in the sequential fashion. So you are accessing the data in the adjacent location. So this is a spatial locality of the data. So if you load in a bunch of data from the next level to the current level, you want to load in the data as a volume. So you want to load in the data together. So because it's very likely that you are going to process those data together, or let's say process those data sequentially. And also temporarily here you will have this sum, right? This is your partial sum when you do this, when you are doing this loop. So every time when you add up, you will save the intermediate results to this partial sum. So that means temporarily you are going to visit this memory to store the partial sum in sequential fashion. So that means temporarily you are going to visit the same location of the data. This is a good example to show the memory locality in the real applications. So that's why when you design the memory system, you need to consider this kind of memory locality when you design the different levels of cache. Any questions? Okay, then let's look at the hierarchical latency analysis in multiple levels of the memory system. So we have so many levels, but for a given memory hierarchy level I, it has a technology intrinsic access time, small ti, but the perceived access time, big Ti, is longer than this small ti. So what does this mean? The perceived access time is the average time you read the data from this level. It may be longer than the technology access time, intrinsic access time, small ti. So what does this mean? This means sometimes when you try to find the data in the current level, you may not be able to find it because they are not there. If they are not there, you have to look for the data from the next level. So here we have this chance to find the data. So here, if we find the data in the current level, we call it a hit. And if you hit the data, you will spend this small ti, this time to access the data. But what if you miss the data? That means you don't find the data in the current level. Then you have to look for the data in the next level. So here we have the probability called hit rate or miss rate for you find the data or you cannot find the data for your hit or miss. And if you miss the data, then you have to look for the next level. So you need to plus the time to look for the data from the next level. So you have another big Ti plus 1. And this one, you have to spend the time here because you don't know whether you will find it or not. So no matter what, even you miss it, you need to spend this small ti to find the data. So I just explained. Even you don't find the data in the current level, you need to spend time to check, right, whether you have it or not. If you don't have it, then you need to go to the next level. No matter what, you need to spend time to find the data. So here, of course, the hit rate and miss rate, when you add up the probability, it will be 1. So you either hit or miss. Therefore, the big Ti is the probability you hit, and then you will have this small ti, or the probability you miss, and then you need to go to the next level, you need to spend this time. And then you can do a simple change here because mi plus hi is 1, so you can combine those two, and then you get this equation. So this is a recursive equation because the access time of this current level depends on, of course, the current level intrinsic access time and miss rate and the access time of the next level. So this is a recursive latency equation as shown here. Of course, you prefer that the perceived access time, the big TI, is close to the intrinsic technology access time, small TI. So how do you achieve that? If you look at this equation, of course, if you make the miss rate low, you don't need to spend time to locate the data from the next level. Then you will approach the intrinsic access time. So how to keep the MI low, the miss rate low? One idea is that you increase the capacity of the current level. Because you increase the capacity of current level, it's more chance that you find the data in the current level. So you don't need to go to the next level to look for the data. But be aware of increasing TI. Because you increase the capacity of the current level, as we discussed earlier, the larger the capacity, the slower the speed. So for the current level, you need to spend more time to locate the data if you increase the capacity of the current level. So you need to be aware of this kind of trade-off. Even though you decrease the MI, but you may increase the TI if you increase the capacity. So that's why it's better to have the multiple levels in the cache. You don't want one level to be super large. So you'd better break that into multiple levels in the system. Another way to keep the miss rate low is to use smarter management policies. So this is related to the computer architecture courses. I will not go into too deep here. If you later take the computer architecture course, then you will learn those cache management policy. So basically, how do you maintain the data in the cache? So which data you prefer to store in the cache? So you will look at your program, your workloads, and then you want to store the most, let's say, mostly visited data in the cache. You can look at you can count the frequency you access those data, and you store only the most frequently used data in the cache. The other policy is that maybe you can do the FIFO, first in, first out. You look at the sequence you access the data. You always store the data you just used in the last few cycles. And then for the cycles way, let's say, earlier, then you abandon those data. So depending on how you manage the data in the cache, because you want to keep the most useful data in this level, and then less useful data in the next level. So this is how you manage to store those data. So it's a topic of the computer architecture course. I will not go in too deep here. So then this is the recursive latency equation, and then we can do one practice here using Intel Pentium 4 processor. Of course, this is an old processor built at 90 nanometer technology node, and the clock frequency is 3.6 gigahertz. So it has L1 cache, 16 kilobytes, and then for the L1 cache, the intrinsic access time is 4 clock cycle, and L2 cache is 1024 kilobytes, and the intrinsic access time is 18 cycles. And at that time, it only has 2 cache because this is old computer. And then after that, we have the main memory. So this processor will have 3 levels of cache. For some high performance processor for the servers, you may even have 4 levels of cache. But mostly 3 levels of cache today. And then the main memory is DRAM, so it has 180 cycles. So let's do some practice. If the miss rate for the level 1 is 0.1, for the level 2 is also 0.1. So you can calculate what is the perceived access time for the level 1 cache and level 2 cache. So how do we do that? So you have to use these recursive equations in the previous slide. And it's recursive, that means you have to do it backwards from the levels in the bottom, backwards, up. So here we assume that you can always find all your data in the main memory. It's large enough to hold all the data of your program. So if you assume that, then the T3 will be the same as this small T3, because you assume all data can be found in this DRAM. Because DRAM is large, like gigabytes. Your image, let's say one image is less than the gigabyte. You can save all the image in the DRAM, but you cannot fit all of them to the L2 cache. So then you have to do it backwards. If you want to get the T2, you need to use this T2 plus M2 T3. So this is the recursive equation, and here you plug in I equals to 2, so you get this one. So you can plug in the M2 and the T3 and T2. If you do that, you get T2 like 36 cycles. And then T1, will be small T1 plus M1 T2. Since you got T2 here already, 36, and then you plug in here 36, and then you have the M1.1 and T1 4. If you do that, you get the next 7.6 cycles. So you have to do it backwards, okay? And you can say that on average, if you have this kind of miss rate, the level 1 cache, on average, you need to spend 7.6 cycles to access 1 bit. And if you do the best, you can get 4 cycles, but due to this kind of miss rate, you can only do 7.6. So this is the example. And of course, you can change those parameters and then redo the examples. I will skip that. So any questions here? Oh, good.